A heat engine is a device that transforms heat energy into useful work. Shown over here to the left is a energy flow diagram. Here's the engine, and it's taking in heat from the hot reservoir through this pipe here. So this QH stands for the input heat. Part of this input heat is converted into useful work, which is represented with a W. And finally, some of the waste heat is expelled to the cold reservoir. So this QC stands for the output heat. Since these reservoirs are quite large, they can give up heat without relatively changing their temperatures. So hence the temperature of the hot reservoir, we'll just label that as TH, and the temperature of the cold reservoir, we'll call that TC. So a basic heat engine is something that transforms the input heat into some work or mechanical energy and expels the remaining amount of energy into the cold reservoir. Now in this process, this requires that heat must flow from the hot reservoir to the cold, which is the basis of the second law of thermodynamics. So let's move down to page 12 in your notes, briefly. There are three possible statements of the second law of thermodynamics, but we're only going to investigate the first one right now. Heat must flow spontaneously from hot to cold and not vice versa. If you've ever placed an ice cube on a table, it soon begins to melt into a puddle of water. And that's because the heat flows from the hot into the cold object and causes it to melt and change state. But have you ever watched a puddle of water freeze back into a block of ice, spontaneously or naturally? No, you wouldn't see that happen because that would violate the second law of thermodynamics, which states that heat must flow spontaneously from the hot to cold, not vice versa. Now you could make it do that, and that is the basis of refrigeration, but we're not investigating that right now. Spontaneously, only heat flows from hot to cold. So going back to heat engines now. So a heat engine in nature essentially capitalizes on the fact that heat flows from hot to cold, and when it moves from that direction, it takes some of that energy and performs useful work. By the conservation of energy, we find that the net work done is equal to the difference, the absolute difference, between the input heat and the output heat. For example, if you had, say, 100 joules of input heat, and then you only had, say, 60 joules of output heat, then the amount of work done must be 40 joules, because 60 plus 40 must add up to 100. The simplest kind of engine that we're going to analyze is one that goes through a cyclic process, a sequence of processes that eventually leaves the substance in the same state where it initially started. If you remember our cyclic process, the change in internal energy is zero, and the first law of thermodynamics stated that the change in internal energy is equal to the heat flow plus the work done. So the work done is equal to the absolute value of the heat flow. And this is the net work done, and this is the net heat flow. So the net heat flow would be the difference between the input heat and the output heat. And typically in our problems, you'll find that the input heat will be considered positive and the output heat will be considered negative, and hence we use absolute value signs in our equation. The thermal efficiency, which is shown down below, is defined as the ratio of the useful work done, W, divided by the initial input heat energy, QH. Another way to look at it is kind of like it's what you get divided by what you put in. And that efficiency will always be less than 1. If you substitute this expression based on the conservation of energy over into here, you can now get another expression written for efficiency. Now remember, the efficiency, when you compute these things, these are all energy. So you can have this in joules, but then this has to be in joules. Or you can have this in a different set of units, say calories, and this has to be in calories, as long as you have the same units on top and on bottom for your efficiency equation. Also, you can use this for rates of heat being done, which is basically joules per second or watts. So there's another way you can rewrite the efficiency ratio. Be very careful with the sign conventions, and that kind of gets confusing. So what we'll do with the efficiency is we'll just simply use an absolute value sign, so you won't have any problems with getting a negative efficiency, which obviously wouldn't make sense. And always make sure that your units are consistent. Okay, you should now be ready to tackle on some sample problems dealing with heat engines and efficiency.